Advanced software design patterns. Advanced software design patterns provide proven solutions to recurring problems in software architecture. These patterns extend beyond basic creational, structural, and behavioral patterns, addressing more complex system-level challenges. Understanding them allows engineers to build more flexible, maintainable, and scalable applications. They facilitate better communication among development teams by establishing a common vocabulary for design solutions. Implementing these patterns effectively can significantly reduce development time and enhance software quality. Developers learn to recognize contexts where specific patterns are most applicable, leading to more robust and adaptable systems. This knowledge is essential for designing large-scale, enterprise-level software. Key advanced patterns include those for concurrency, messaging, and distribution. For instance, the actor model helps manage concurrent operations by isolating state and promoting message passing. The saga pattern addresses distributed transactions, ensuring data consistency across multiple services. Other patterns, like circuit breaker, enhance resilience in distributed systems by preventing cascading failures. These patterns are particularly relevant in microservices and cloud-native environments where distributed computing is prevalent. Mastering these advanced patterns is a hallmark of experienced software architects and senior engineers. Microservices architecture principles. Microservices architecture is an approach to developing a single application as a suite of small services, each running in its own process and communicating with lightweight mechanisms. These services are built around business capabilities and are independently deployable by fully automated deployment machinery. This architectural style promotes agility, scalability, and resilience in complex systems. Each microservice focuses on a specific function, allowing for specialized development and deployment. This modularity reduces the impact of failures, as a problem in one service does not necessarily bring down the entire application. It also enables teams to choose the best technology stack for each service. Key principles of microservices include single responsibility, bounded contexts, and autonomous teams. Single responsibility dictates that each service should do one thing well, minimizing its scope and complexity. Bounded contexts define clear boundaries around data and business logic, preventing services from becoming overly coupled. Autonomous teams are empowered to develop, deploy, and operate their services independently, fostering rapid innovation. While offering significant benefits, microservices also introduce challenges such as distributed data management, inter-service communication overhead, and operational complexity. Careful design and robust tooling are essential for successful implementation. Cloud-native development practices. Cloud-native development is an approach to building and running applications that fully leverage the advantages of the cloud computing delivery model. It emphasizes speed, agility, and resilience, enabling organizations to build and deploy applications rapidly and reliably. This paradigm involves using technologies like containers, microservices, immutable infrastructure, and declarative APIs. Cloud-native applications are designed to be highly scalable, fault-tolerant, and easily manageable in dynamic, distributed environments. They are built to thrive in the cloud, rather than simply being lifted and shifted from traditional on-premise infrastructure. This approach fundamentally changes how software is conceived, developed, and operated. Core practices include continuous delivery, DevOps, and a strong focus on automation. Continuous delivery ensures that software can be released reliably and frequently, often multiple times a day. DevOps principles integrate development and operations to streamline the entire software lifecycle, fostering collaboration and shared responsibility. Automation is paramount, covering everything from infrastructure provisioning to testing and deployment, minimizing manual errors and accelerating processes. Cloud-native development also promotes observability, allowing teams to monitor and understand the behavior of their applications in production. These practices collectively enable organizations to deliver value faster and adapt more quickly to market changes. Containerization with Docker. Docker is a platform that uses OS-level virtualization to deliver software in packages called containers. Containers are lightweight, standalone, executable packages of software that include everything needed to run an application: code, runtime, system tools, system libraries, and settings. They ensure that an application runs consistently across different environments, from development to staging to production. This solves the "it works on my machine" problem by encapsulating dependencies. Docker has revolutionized application deployment by making it faster, more reliable, and more efficient. It allows developers to package applications and their dependencies into a single unit, simplifying deployment and scaling. The benefits of Docker containerization are numerous, including portability, efficiency, and isolation. Portability means a container can run virtually anywhere, on any machine with Docker installed, without modification. Efficiency comes from sharing the host OS kernel, making containers much lighter than traditional virtual machines. Isolation ensures that applications and their dependencies are separated, preventing conflicts and improving security. Docker also provides a robust ecosystem with tools for building, managing, and orchestrating containers, such as Docker Compose for multi-container applications. Learning Docker is a fundamental skill for any modern software engineer working with cloud-native applications. Orchestration with Kubernetes. Kubernetes is an open-source container orchestration system for automating deployment, scaling, and management of containerized applications. It groups containers that make up an application into logical units for easy management and discovery. Kubernetes provides a framework to run distributed systems resiliently, handling tasks like service discovery, load balancing, storage orchestration, and automated rollouts and rollbacks. It abstracts away the underlying infrastructure, allowing developers to focus on application logic rather than operational complexities. This powerful platform has become the de facto standard for managing containers in production environments, especially for microservices architectures. The core components of Kubernetes include the master node and worker nodes. The master node manages the cluster, scheduling workloads, and maintaining the desired state. Worker nodes run the actual containerized applications, managed by agents like Kubelet. Key features like pods, deployments, and services enable robust application management. Pods are the smallest deployable units, encapsulating one or more containers. Deployments manage the lifecycle of pods, ensuring desired replicas and enabling updates. Services provide a stable network endpoint for pods, facilitating communication and load balancing. Understanding Kubernetes is crucial for deploying and managing scalable, resilient applications in the cloud. DevOps principles and practices. DevOps is a set of practices that combine software development, dev, and IT operations, ops, to shorten the system's development lifecycle and provide continuous delivery with high software quality. It aims to unify software development and software operation. The main goal of DevOps is to foster a culture and environment where building, testing, and releasing software can happen rapidly, frequently, and more reliably. It emphasizes communication, collaboration, integration, and automation throughout the software delivery pipeline. This cultural shift breaks down traditional silos between development and operations teams, promoting shared responsibility and faster feedback loops. Key principles of DevOps include culture, automation, lean, measurement, and sharing, CALMs. Culture focuses on collaboration and trust between teams. Automation streamlines repetitive tasks across the entire lifecycle, from code commit to deployment. Lean principles aim to eliminate waste and optimize flow, delivering value efficiently. Measurement involves tracking metrics to monitor performance and identify bottlenecks, enabling continuous improvement. Sharing promotes knowledge exchange and collective learning, fostering a continuous improvement mindset. Implementing DevOps practices leads to faster time to market, improved system stability, and enhanced team productivity. Continuous integration/deployment, CI/CD. Continuous integration, CI, is a development practice where developers frequently merge their code changes into a central repository, after which automated builds and tests are run. The primary goal of CI is to detect and address integration errors as quickly as possible. By integrating frequently, developers can identify conflicts and bugs early in the development cycle, reducing the complexity and cost of fixing them. Each merge triggers an automated process that compiles the code, runs unit tests, and performs other checks to ensure the new code integrates seamlessly with the existing code base. This practice significantly improves code quality and reduces integration headaches. Continuous delivery, CD, is an extension of CI, ensuring that software can be released to production at any time. It automates the entire software release process, from code commit to deployment in various environments, staging, production. Continuous deployment takes CD a step further by automatically deploying every change that passes all stages of the production pipeline to production without human intervention. The benefits of CI/CD include faster release cycles, improved software quality, reduced risk, and increased developer productivity. Implementing a robust CI/CD pipeline is a cornerstone of modern software engineering and DevOps practices, enabling rapid and reliable software delivery. Automated testing strategies. Automated testing is a critical component of modern software development, involving the use of software tools to execute tests, compare actual outcomes with predicted outcomes, and report on the success or failure of tests. This approach significantly speeds up the testing process, allowing for more frequent and thorough validation of code changes. It reduces the need for manual intervention, freeing up human testers to focus on more complex exploratory testing. Automated tests are repeatable, consistent, and can be run as part of a CI/CD pipeline, providing immediate feedback on code quality. This early detection of defects is crucial for maintaining a high-quality code base. Various automated testing strategies exist, forming a testing pyramid or testing trophy. Unit tests form the base, testing individual components or functions in isolation. Integration tests verify that different modules or services work together correctly. End-to-end, E2E, tests simulate user scenarios across the entire application, ensuring the system behaves as expected from a user's perspective. Other types include performance tests, security tests, and accessibility tests. Each layer of the pyramid serves a specific purpose, with a higher volume of fast, inexpensive unit tests at the bottom and fewer, slower, more expensive E2E tests at the top. A balanced strategy across these layers ensures comprehensive coverage and robust software. Performance testing and optimization. Performance testing is a non-functional testing technique used to determine the speed, responsiveness, and stability of a computer, network, software program, or device under a particular workload. It evaluates how a system behaves under various load conditions, identifying bottlenecks and areas for improvement. Key metrics include response time, throughput, and resource utilization, CPU, memory, network. This type of testing is crucial for ensuring that applications can handle expected user traffic and maintain a smooth user experience. Without adequate performance testing, applications can suffer from slow response times, crashes, and poor scalability, leading to user dissatisfaction and business loss. Optimization involves refining code, architecture, and infrastructure to improve performance characteristics identified during testing. Techniques include caching, database query optimization, load balancing, and efficient algorithm design. Caching frequently accessed data reduces the need for repeated computations or database calls. Optimizing database queries ensures data retrieval is fast and efficient. Load balancing distributes incoming traffic across multiple servers, preventing any single server from becoming overwhelmed. Efficient algorithms reduce computational complexity and resource consumption. Continuous monitoring and iterative optimization are essential to maintain high performance as systems evolve and user demands increase. Security best practices in software. Software security is paramount in today's digital landscape, protecting applications from malicious attacks and ensuring data integrity and confidentiality. Implementing security best practices throughout the software development lifecycle, SDLC, is crucial rather than treating security as an afterthought. This proactive approach, often termed security by design, integrates security considerations from the initial design phase through deployment and maintenance. Common vulnerabilities include injection flaws, broken authentication, sensitive data exposure, and cross-site scripting, XSS. Developers must be aware of these threats and employ defensive coding techniques to mitigate risks. Regular security audits and penetration testing are also vital to identify and address weaknesses. Key best practices include input validation, secure coding guidelines, access control, and encryption. Input validation prevents malicious data from entering the system, guarding against injection attacks. Adhering to secure coding guidelines, such as OWASP Top 10, helps developers avoid common pitfalls. Implementing robust access control mechanisms ensures that users only have permissions necessary for their roles, following the principle of least privilege. Encryption protects sensitive data both in transit and at rest, preventing unauthorized access. Regular security training for development teams and staying updated on the latest threats are also essential components of a comprehensive security strategy, fostering a security-conscious culture. API design and development. Application programming interfaces, APIs, are fundamental building blocks of modern software, enabling different software systems to communicate and interact with each other. A well-designed API is crucial for the success of any software product, as it dictates how easily other developers can integrate with and utilize the service. Good API design prioritizes clarity, consistency, and usability, making the API intuitive and easy to understand. It involves careful consideration of resource naming, HTTP methods, status codes, and data formats. Poorly designed APIs can lead to integration challenges, increased development time, and frustration for consumers. The goal is to create a contract that is both powerful and simple to use. Two prevalent API styles are RESTful APIs and GraphQL. REST, representational state transfer, APIs are stateless, client-server architectures that use standard HTTP methods, get, post, put, delete, to manipulate resources. They are widely adopted due to their simplicity and scalability. GraphQL, on the other hand, is a query language for APIs and a runtime for fulfilling those queries with existing data. It allows clients to request exactly the data they need, reducing overfetching and underfetching. While REST is resource-oriented, GraphQL is data-oriented. The choice between REST and GraphQL depends on specific project requirements, data complexity, and client needs. Both require careful design to ensure maintainability and performance. Event-driven architectures. Event-driven architecture, EDA, is a software architecture paradigm promoting the production, detection, consumption of, and reaction to events. An event is a significant change in state, such as an item being added to a shopping cart or a payment being processed. In an EDA, components communicate asynchronously by emitting and reacting to events rather than making direct calls. This decoupling of services enhances scalability, resilience, and responsiveness, especially in distributed systems. It allows services to operate independently, reducing tight coupling and making the system more adaptable to change. EDA is particularly well suited for microservices and real-time data processing scenarios. Key components of an EDA include event producers, event consumers, and an event broker or message queue/stream. Event producers generate events and publish them to the broker. The event broker acts as an intermediary, reliably delivering events to interested consumers. Event consumers subscribe to specific event types and react to them, performing their designated tasks. Common technologies for event brokers include Apache Kafka, RabbitMQ, and Amazon Kinesis. While EDAs offer significant advantages in terms of scalability and flexibility, they also introduce complexities related to event ordering, idempotency, and distributed tracing. Careful design and robust monitoring are essential for successful implementation. Serverless computing concepts. Serverless computing is a cloud execution model where the cloud provider dynamically manages the allocation and provisioning of servers. Developers write and deploy code without worrying about the underlying infrastructure. The cloud provider automatically scales the application up or down based on demand, and users only pay for the compute time consumed, not for idle server capacity. This pay-per-execution model can significantly reduce operational costs and overhead. Functions as a Service, FaaS, is a common serverless offering, where developers deploy individual functions that are triggered by events, such as an HTTP request or a database change. This paradigm shifts operational responsibility from the developer to the cloud provider. Benefits of serverless computing include reduced operational costs, automatic scaling, and faster time to market. Developers can focus purely on writing code, accelerating development cycles. Automatic scaling ensures applications can handle fluctuating workloads without manual intervention. The pay-per-execution model makes it cost-effective for applications with unpredictable or intermittent traffic. However, serverless also introduces challenges, such as vendor lock-in, cold starts, initial latency for infrequently used functions, and debugging complexities across distributed functions. Popular serverless platforms include AWS Lambda, Azure Functions, and Google Cloud Functions. Understanding these trade-offs is crucial for deciding when serverless is the right choice for a project. Database design for scalability. Designing databases for scalability is critical for applications that need to handle large volumes of data and high user traffic. Traditional relational databases can become bottlenecks under heavy load, necessitating strategies to distribute data and queries. Scalability in databases refers to their ability to handle increased workload by adding resources, either vertically, more powerful server, or horizontally, more servers. Horizontal scaling, often achieved through sharding or partitioning, is generally preferred for cloud-native and distributed applications. Effective database design for scalability ensures consistent performance and availability as an application grows, preventing slowdowns and outages. NoSQL databases are often chosen for their inherent scalability and flexibility compared to traditional relational databases. They come in various types. Document databases, e.g. MongoDB, for flexible, semi-structured data. Key value stores, e.g. Redis, for high-speed data retrieval. Column family databases, e.g. Cassandra, for large-scale distributed data. Graph databases, e.g. Neo4j, for highly connected data. Each type offers different strengths for specific use cases. Distributed databases further enhance scalability by spreading data across multiple nodes, often in different geographical locations, improving fault tolerance and reducing latency. Understanding the trade-offs between consistency, availability, and partition tolerance, CAP theorem, is fundamental when designing scalable database solutions. Big Data Technologies Introduction. Big data refers to extremely large datasets that may be analyzed computationally to reveal patterns, trends, and associations, especially relating to human behavior and interactions. These datasets are characterized by the 3 V's: volume, velocity, and variety. Volume refers to the immense amount of data generated. Velocity describes the speed at which data is generated and processed. Variety encompasses the diverse types of data, from structured to unstructured. Traditional data processing applications are inadequate for handling such vast and complex data. Big data technologies provide the tools and frameworks necessary to store, process, and analyze these massive datasets, unlocking valuable insights. Key big data technologies include distributed storage systems like Hadoop Distributed File System (HDFS) and processing frameworks such as Apache Spark. HDFS allows for reliable, scalable storage of large files across clusters as commodity hardware. Apache Spark provides fast, general-purpose cluster computing for large-scale data processing, supporting various workloads like batch processing, stream processing, and machine learning. Other technologies like Apache Kafka are used for real-time data streaming, while NoSQL databases handle flexible data storage. Understanding these technologies is crucial for engineers working with data-intensive applications and analytics, enabling them to build scalable and efficient data pipelines. Machine learning in software engineering, MLOps. MLOps, machine learning operations, is a set of practices that aims to deploy and maintain machine learning models in production reliably and efficiently. It bridges the gap between data science and operations, similar to how DevOps bridges development and operations. MLOps encompasses the entire lifecycle of an ML model, from data preparation and model training to deployment, monitoring, and retraining. The goal is to automate and streamline the process of taking ML models from experimentation to production, ensuring reproducibility, versioning, and continuous improvement. This discipline is essential for realizing the full potential of machine learning in real-world applications, moving beyond isolated experiments. Key aspects of MLOps include data versioning, model versioning, automated ML pipelines, and continuous monitoring. Data versioning ensures that the data used for training and evaluation is tracked and reproducible. Model versioning allows for managing different iterations of models and their associated metadata. Automated ML pipelines orchestrate the steps from data ingestion to model deployment, enabling rapid iteration and deployment. Continuous monitoring tracks model performance in production, detecting data drift, concept drift, and performance degradation, triggering retraining or model updates as needed. Implementing MLOps practices is crucial for building robust, scalable, and maintainable AI-powered systems, ensuring that ML models deliver consistent value over time. Advanced version control with Git. Git is a distributed version control system that tracks changes in source code during software development. While basic Git commands are widely known, advanced Git techniques are essential for managing complex projects, collaborating effectively in large teams, and maintaining a clean, coherent commit history. These advanced techniques go beyond simple commit, push, and pull operations, enabling more sophisticated workflows. Understanding them helps prevent merge conflicts, simplifies code reviews, and makes it easier to revert changes or explore historical states of the codebase. Mastery of advanced Git is a hallmark of professional software engineers, ensuring efficient and error-free collaboration. Key advanced Git concepts include rebasing, cherry-picking, reflog, and Git hooks. Rebasing allows developers to rewrite commit history, creating a cleaner, linear project history by moving or combining commits. Cherry-picking enables selecting individual commits from one branch and applying them to another, useful for hotfixes or specific feature transfers. Git reflog records all changes to the tips of branches and other references, providing a safety net to recover lost commits. Git hooks are scripts that Git executes before or after events like committing or pushing, enabling automation of tasks like code linting or testing. These tools empower developers to manage their repositories with greater precision and control, streamlining complex development workflows. Code quality and refactoring. Code quality refers to the characteristics of software that affect its maintainability, readability, testability, and overall health. High-quality code is easier to understand, modify, and extend, reducing the cost of ownership and accelerating future development. It adheres to established coding standards, design principles, and best practices. Poor code quality, often referred to as technical debt, can lead to increased bugs, slower development cycles, and difficulty in onboarding new team members. Ensuring high code quality is a continuous process that involves static analysis, code reviews, and adherence to coding guidelines. It is a shared responsibility of the entire development team. Refactoring is the process of restructuring existing computer code without changing its external behavior. The primary goal of refactoring is to improve the non-functional attributes of the software, such as readability, maintainability, and complexity. Common refactoring techniques include extracting methods, renaming variables, consolidating duplicate code, and simplifying conditional expressions. Refactoring should be done incrementally and frequently, ideally as part of the daily development cycle, rather than in large disruptive refactoring sprints. Tools like static code analyzers and IDE features assist developers in identifying refactoring opportunities and performing changes safely. Regular refactoring is crucial for keeping the codebase healthy and preventing the accumulation of technical debt, making it easier to adapt to new requirements. Software project management methodologies. Effective software project management is crucial for delivering successful software products on time, within budget, and to specification. It involves planning, organizing, securing, and managing resources to achieve specific goals. Various methodologies provide frameworks for structuring and executing software projects, each with its own strengths and weaknesses. The choice of methodology often depends on project size, complexity, team structure, and client requirements. Understanding these different approaches allows project managers and teams to select the most appropriate framework for their specific context, optimizing for efficiency and desired outcomes. Good project management minimizes risks and maximizes value delivery. Agile and Scrum are two of the most widely adopted methodologies in modern software development. Agile is an iterative and incremental approach, emphasizing flexibility, collaboration, and customer feedback. It values responding to change over following a rigid plan. Scrum is a specific framework within Agile, characterized by short development cycles called sprints, daily stand-up meetings, and defined roles like product owner, Scrum Master, and development team. Other methodologies include waterfall, linear, sequential, Kanban, visual workflow management, and lean, eliminating waste. Each methodology offers a structured way to manage the complexities of software development, promoting efficiency and adaptability. Technical debt management. Technical debt in software development is a concept that reflects the extra development work that arises when code that is easy to implement in the short run is used instead of applying the best overall solution. It's like financial debt. If not repaid, it can accumulate interest, making future changes more difficult and costly. Technical debt can manifest as poorly structured code, lack of documentation, outdated libraries, or insufficient testing. While sometimes incurred intentionally to meet tight deadlines, it often arises unintentionally due to rushed development or evolving requirements. Unmanaged technical debt significantly slows down development velocity and increases the risk of bugs and system instability. Effective technical debt management involves identifying, prioritizing, and systematically addressing debt. Tools like static code analyzers can help identify code smells and potential debt. Prioritization should consider the impact of the debt on future development, system stability, and user experience. Strategies for repayment include dedicated refactoring sprints, incorporating small refactoring tasks into daily development, the Boy Scout rule, and establishing clear coding standards. It's crucial to balance new feature development with debt repayment to maintain a healthy code base. A proactive approach to technical debt management ensures the long-term maintainability and agility of a software system, preventing it from becoming a crippling burden. Observability and monitoring. Observability is the ability to infer the internal states of a system by examining its external outputs. It goes beyond traditional monitoring by providing deeper insights into why a system is behaving in a certain way, not just that it is behaving that way. Key pillars of observability include logs, metrics, and traces. Logs provide detailed, time-stamped records of events within an application. Metrics are numerical measurements captured over time, such as CPU utilization or request latency. Traces track the journey of a request as it flows through multiple services, providing an end-to-end view of its execution. Together, these pillars enable engineers to understand complex distributed systems and troubleshoot issues effectively. Monitoring, while related, typically focuses on known unknowns, predefined metrics, and alerts for expected failures. Observability addresses unknown unknowns, allowing engineers to ask arbitrary questions about the system's behavior without prior knowledge of what might go wrong. Implementing robust observability involves instrumenting applications to emit rich telemetry data and using specialized tools for data collection, storage, and analysis. This includes platforms like Prometheus for metrics, Elasticsearch for logs, and Jaeger or Zipkin for traces. A well-implemented observability strategy is crucial for maintaining the health, performance, and reliability of modern distributed software systems, especially in cloud-native environments. Site Reliability Engineering (SRE) concepts. Site Reliability Engineering (SRE) is a discipline that incorporates aspects of software engineering and applies them to infrastructure and operations problems. The main goals of SRE are to create highly reliable and scalable software systems. SRE teams use software as a tool to manage systems, automate operational tasks, and measure reliability. This approach treats operations as a software problem, leading to more robust, predictable, and efficient system management. It emphasizes a data-driven approach to reliability, using metrics like service-level objectives, SLOs, and error budgets to guide decision-making. SRE is crucial for maintaining the uptime and performance of critical services. Key SRE practices include error budgets, toil reduction, and postmortems. An error budget defines the acceptable amount of unreliability for a service, allowing teams to balance innovation with stability. Toil refers to manual, repetitive, automatable operational work. SRE aims to eliminate or automate toil to free up engineers for more impactful work. Postmortems are blameless analyses of incidents, focusing on identifying root causes and implementing preventative measures rather than assigning blame. These practices foster a culture of continuous improvement and learning from failures. SRE is a highly sought-after discipline that combines deep technical expertise with a strong focus on operational excellence and system resilience. Ethical considerations in software engineering. As software increasingly permeates every aspect of society, software engineers bear a significant ethical responsibility for the products they create. Ethical considerations involve understanding the potential societal impact of software, both positive and negative, and making conscious decisions to mitigate harm. This includes issues like data privacy, algorithmic bias, accessibility, and the responsible use of AI. Engineers must consider how their software might be misused, who might be excluded, and what unintended consequences could arise. A strong ethical compass is essential for building trustworthy and beneficial technology. Ignoring these considerations can lead to significant societal harm and erode public trust in technology. Key ethical principles guide software engineers in their work. These often include prioritizing public safety and welfare, avoiding harm and minimizing negative impact, protecting privacy and data security, ensuring fairness and preventing discrimination, e.g., algorithmic bias, promoting transparency and accountability, respecting intellectual property. Adhering to these principles requires critical thinking, open discussion, and sometimes advocating for ethical choices within development teams and organizations. Integrating ethical considerations into the software development lifecycle, from design to deployment, ensures that technology serves humanity responsibly and equitably. This proactive approach helps build a more just and inclusive digital future. Software licensing and open source software. Licensing defines the legal rights and restrictions governing the use, distribution, and modification of software. It is a critical aspect of software development, impacting everything from intellectual property protection to collaboration models. Understanding different license types is essential for both developers creating software and organizations using it. Licenses ensure that creators retain control over their work while enabling others to use it under specified terms. Failing to comply with licensing agreements can lead to legal disputes and financial penalties. This legal framework underpins the entire software ecosystem, from proprietary products to open source projects. Open source software, OSS, is software with source code that anyone can inspect, modify, and enhance. It is typically distributed under licenses that grant users the freedom to run, study, change, and distribute the software and its modified versions. Common open source licenses include MIT license, permissive, minimal restrictions; Apache license 2.0, permissive with patent grants; GNU General Public License, GPL, copyleft, requires derivatives to be open source. The choice of open source license has significant implications for how the software can be used and integrated into other projects. Open source fosters collaboration, innovation, and transparency, driving much of the modern technological landscape. However, developers must be mindful of license compatibility and obligations when combining different open source components. Career development for software engineers is a continuous journey involving skill enhancement, professional growth, and strategic planning. The rapidly evolving technology landscape demands constant learning and adaptation. Beyond technical proficiency, soft skills like communication, teamwork, and problem-solving are increasingly vital for career progression. Engineers must actively seek opportunities to expand their knowledge, take on new challenges, and contribute to impactful projects. Networking with peers, mentors, and industry leaders can open doors to new possibilities and provide valuable insights. A proactive approach to career development ensures long-term success and fulfillment in the dynamic field of software engineering. Key aspects of career development include continuous learning and skill acquisition, e.g., new languages, frameworks, cloud platforms; mentorship and peer learning; building a strong professional network; developing leadership and communication skills; specializing in a niche or becoming a generalist; T-shaped engineer; contributing to open source projects or personal portfolios; setting clear career goals, regularly assessing progress, and adapting strategies are essential. Whether aspiring to be a technical lead, architect, or individual contributor, a well-defined career path and commitment to growth are paramount. The software engineering profession offers diverse opportunities, and continuous development is the key to unlocking them. Future trends in software engineering. The field of software engineering is constantly evolving, driven by rapid technological advancements and changing societal needs. Staying abreast of future trends is crucial for engineers to remain relevant and contribute to innovation. Emerging areas like artificial intelligence, quantum computing, Web3, and advanced cybersecurity are reshaping how software is designed, developed, and deployed. These trends present both exciting opportunities and significant challenges, requiring engineers to adapt their skill sets and embrace new paradigms. Understanding these trajectories helps in making informed career choices and preparing for the next generation of software systems. The pace of change is accelerating, making continuous learning more important than ever. Key trends shaping the future include pervasive AI and machine learning. MLOps, AI-powered development tools, increased adoption of serverless and edge computing, quantum computing's nascent impact on complex problem-solving, enhanced cybersecurity measures and privacy-preserving technologies, the rise of Web3, blockchain, and decentralized applications, more sophisticated low-code, no-code platforms, sustainable software engineering practices. These trends will drive demand for specialized skills in areas like AI ethics, quantum algorithms, and decentralized system design. Software engineers who can navigate these evolving landscapes, integrate new technologies, and prioritize ethical considerations will be at the forefront of innovation, shaping the digital world of tomorrow.